Hello Professor, my name is Vora and I am here to present the analysis of an envelope detector, which is a device used in communication systems for my ELL101 project. Communication systems are responsible for the transmission and reception of signals. The process involves first converting the original signal to a form that can be transmitted over long distances, then receiving the signal, amplifying it to an appropriate amplitude, and finally converting it back to the original signal for further processing and use. If the original signal is a relatively lower frequency, then it is prone to much disturbance while passing over long distances. Therefore, we use a high frequency carrier wave on which the signal is modulated as an envelope. This makes the final signal of the form of A sine omega 1t times sine omega 2t, where omega 1 is the frequency of the original signal while omega 2 is the frequency of the carrier wave. And here we can see that the original signal is retained as the envelope of the final signal which is transmitted. So the envelope detector is a device which is used after signals are received to filter out the high frequency carrier wave and output the envelope, which is the original signal. It has two components, a diode and a capacitor and resistor system that acts as an RC circuit. It performs two principal functions, that are rectification and envelope detection. The rectification of the signal is performed by a diode. It is required to remove negative voltages and allow only the positive part to appear across the capacitor, as the envelope detection in the next step by the capacitor is not possible for the AC signal. For example, in an AC RC circuit, the voltage only gets phase shifted. Assuming that the diode is ideal with zero cutoff voltage, the V across the capacitor is V input, which is plus V when V is greater than 0, and the V across the capacitor remains 0 when the V is less than 0 in the input signal. However, in the case that we use a silicon diode, which is a real diode, and that is what is actually used, there will be a signal transmitted across the capacitor only for the voltage greater than 0.7 volts, and this will not cause much change except for the fact that the final signal will be shifted along the y-axis by 0.7 volts, and this can be easily taken care of in further processing. So the negative part of the signal is removed and only the positive part remains, thus we can proceed for the next step. Envelope detection, which is filtering. The rectified input from the diode is now across the RC parallel circuit. The time constant of this RC combination is chosen very high so that the high frequency fluctuations in the input voltage cause very less change in the output. That is the voltage across the capacitor, which is proportional to the charge on the capacitor plates. This is because in a small time duration, the change in V is proportional to e to the power minus t by RC times V naught, which is extremely small as t is small and RC is somewhat high as well. For the modulating signal, which is low frequency, the capacitor voltage change will be significant because then t is not small enough, and therefore the voltage, this signal is not filtered. So the voltage on the capacitor will almost remain equal to the amplitude of the wave at every instant. Thus it will finally trace out the envelope. For instance, here we see two portions. One portion is where the diode is conducting. However, when the diode is turned off, there is slight decrease in the capacitor voltage, but it is small enough that we can ignore it and treat the whole output as an envelope. To conclude, therefore, the diode rectifies the signal so that the envelope detection by filtering is possible, and the RC circuit takes this rectified signal and filters the high frequency carrier signal out of it, retaining only the low frequency original modulating signal. These two components therefore together form an envelope detector, which is of great use in communication systems today. Thank you.